Okay, let's go through the question 1. Okay, the first is we want to find the estimate. So usually you can find like the MLE or the manifold moment. And let's try manifold moment. Okay, so the average of x is equal to like this. Interval from -1 to 1 x this. Okay. Okay. So this is equal to this plus 1/2 theta x squared. And we know that it can be that 4x squared plus 6 theta x to the power 3 -1 to 1. So that will be this one is 0 and this one is a 2, 3. This. Oh, sorry, it's this. Yes, 1 minus 1, 2. Oh, yeah. So that means, okay, so this is equal to, that means the S bar, if but 3, the is 3 times S bar. Okay. And then by the law of large number, S bar will converge to this. So 3S bar will converge to theta. Okay. That means it's consistent. Okay. Okay, in question 2, we have the S1 to Sn table where
it was just a factor of 3 that was missing in the integral, but I think it's fine now.
which one? Sorry.
So the primitive of x squared is x cubed divided by 3.
It's 2 divided by 3.
Oh, you have a 6 there. No, it's fine. Okay, yeah, my mistake.
Okay, okay. Yeah. 6. Because here is 1/2. So it's,
Yeah, all good. Thanks.
yeah, okay.
Can I ask a
So,
question about this?
okay.
So how did you know to use the method of moments here instead of the MLE?
Okay. Because therefore is much easier to calculate.
Yeah.
So
I mean,
always try method of moment first. Yeah. Usually
Okay.
method of moment will be a consistent estimate. Yeah.
Okay.
Yeah. Because we can have the log large number, and so usually we will have this, the average of x will equal to some function of g of theta. So if the g of theta G, the function G is continuous, if the G inverse is continuous, then that means the G inverse X bar, we can apply the continuous matrix theory. Maybe. And the law of large number to say this one is a consistent estimator. Okay. And that is usually we can have this property. So you can use this two theory to show that this is a consistent estimator. Yeah.
Okay, thanks.
Okay. Yeah, CMLE also can also work in this case. Yeah, this is a very good. This is a exponential family, so the MLE will always consistent.
Yeah, I think that, I mean, I possibly could have just been doing it wrong, but I think the MLE here is really difficult to find, which is.
I'm not sure. I haven't calculated. I didn't calculate. Yeah.
Yeah.
Yeah,
Okay.
Sam, I found the same
Okay.
to be true.
Okay.
Yeah. Okay. And the second one is we have three different types of estimator, and we want to estimate the mu square. Okay. We can show that all these three methods are consistent. Like this one is equal to like the variance of S bar minus this. Okay. And the variance S bar is equal to no, S bar square. No, I don't need this. Okay, let's say we know S bar will converge to mu. So S bar square will converge to mu square. Okay. And so that means T1 n is consistent. And for T2n, S bar square will converge to mu square. And S square will converge to sigma square. Okay. So this one will converge to this, which is needle. Okay. And T3n is also the same. Okay. And now we want to calculate the asymptotic variance. Okay. Okay. So we have this one, S bar. Okay. Plus.
No, it was when you wrote the expectation of X bar square is equal to variance of X bar.
Oh, okay. Yeah, that's plus.
Yeah.
Thank you. And yeah, so now we have these three. I want to show that the asymptotic variance is the same. Sorry, this square is plus square. And the condition is mu is not equal to 0. Okay. So that means the mu square is positive. So these two will convert to a positive value, and these two will convert to 0. So the T2n and T3n will go the same in probability. Okay. One way to do that is like this. Let's calculate the starting values of T1n first. So the T1n, we want to use a delta method. So it's a S bar minus the mu square of n. This one is equal to, can be approximated by, this is delta method. Like this. We find the first derivative, so it's 2 mu S bar minus mu. Okay. So you think like the G of mu is equal to mu square. And we have to prove this is the first derivative of mu. Okay. First derivative of G of mu. Okay. So this can be approximated by the standard normal distribution, little, and the variance of S, so it should be sigma square and 4 mu square. Okay. And what I want to show here is the square root of n of T1n minus T2n. This will converge to 0. So that means if this is true, then that implies the value, the starting values of T1n and T2 are all the same. So how do I say? Okay. So let's calculate this. This is equal to like the S squared. Okay. And this is equal to this. And we know that S squared will converge to sigma square. So this term will converge to 0. Okay. In probability. Okay. And for T3, we can do the same thing. Okay. So is this. Okay, we have the maximum of this, so that means okay. Want to show this go to 0 and in probability. Okay, so we can say So what I want to do is this, the probability of this. Not equal to 0. If this one goes to 0, then we will have this one. So and this is equal to the event like the s bar square minus s square divided by n if smaller than 0. Okay. Yeah, otherwise the T21 equal to T2. So how about I say this? N equal to T2n. And this is equal to probability of the square minus s square divided by n smaller than 0. Okay. And because s bar square converges to mu square and converge to 0, so the probability converges to 0. Okay. So that means we have the converge, we have the stop. Okay. So they will have the same asymptotic values. Okay. Yeah. Okay. And the B is want to find asymptotic value for mu is not equal to 0. So we just show that it should be like this one. Okay. So it's a 4 square. And for C, we want to find the when mu is equal to 0. Okay. QC. Okay. So let's say this one is T1n is equal to S bar squared. Okay. So if mu is equal to 0, then this will converge to 0. Converge to mu square, which is 0. Okay. So that means, and we also know that the S bar minus mu multiply square root of n. This will converge to this. So this is central limit theory. And because mu is equal to 0, so this is equal to this. Okay. Okay. Yeah. So the n multiplies this one is equal to square root of the S bar. This. So we will have this will converge to the sigma square chi square 1. Yeah, because let's do here we have a sigma here, sigma square. So this one is the chi square 1. So the total is the sigma square chi square 1. Okay. Okay. 1. And then we want to find the T2n. Okay. Okay, the T2n is equal to S bar square minus S squared. Yes. Okay. Let's do the same thing. We find this one, the distribution of this theta. Is equal to n s bar square minus s square. Okay. So from the first part, we know that this is equal to chi square sigma square. Distribution. Okay. Because the s square converges to sigma square. Okay. Okay. And for the third one, okay, we want to find the n t3 n3 t3n. This is equal to n t2n maximum n t2n 0. Okay. Yeah. So this will converge distribution to maxima sigma square chi square 1 minus sigma square 0. Okay. So we have the 3 versatile distribution. Okay. Any questions so far? So this just the central limit theory and some calculation. Yeah. Okay. And then we want to figure out which one is better. Okay. Okay, so for a way to measure the performance of the estimate is you can I would say this one is better than this one because this estimate have the you can see the chi-square is always positive. So that is in like the asymptotic bias. So we know that the S bar square will converge to 0, but the n S bar square will converge to a positive value. So that may create some bias. And this one is unbiased because the mean of a chi-square 1 is equal to 1. So this is mean 0. This is always positive. And if you want to measure this, you can find we know this one will converge to small square chi-square 1. So we measure this. Okay, so this is the variance of chi-square will converge to this. Then we can measure also the variance of the asymptotic distribution. The second moment asymptotic distribution. So this is the second moment, and this is the variance. And this one is always greater than this one. Okay.
So, Chi, is it fair to say that the best one's always going to be the one with the minimum variance? Like you're never going to use a different metric.
Okay. You mean this one? This what I do here just like we know T1 will convert to 0. So the difference of this is an error we make. So this is mean square error. So then we know the NT1 converge to this. And we use this one. This is like the mean square error. Okay. Okay, say or you can say as a total mean square error. Yeah. So that's the idea. Yeah, it's not here. So okay. And like yeah. If we want to, we have this estimator, the target is 0. So we usually use this this is a mean square error. And this is, but if we measure this, everyone is 0. So what we do is we multiply n in here. Or you can say we multiply n squared in here. So instead we use this one, n squared t1 minus d0 squared. So we multiply n squared, so the quantity will become bigger. This is always okay. So this is always converged to 0 for like k equal to 1, 2, 3. So then we can have this square. And we know this one can be approximated by the sigma square k square 1 minus 0 square. And this, so this is quantity of the second moment of the k square distribution. This, okay. And we do the same thing for T2 and T3. So this is the answer of T2. And for T3, okay, I see T3 is will be complicated, but oh, it's the same, just like this. The maxima sigma square square. So this is T3. Okay. So this is equal to sigma to the power 4 and maxima of okay. And the asymptotic variance of asymptotic mean square root of T3 will be smaller than T2. So the T2 is this. This is equal, T2 is this one. Because we truncate all the values smaller than 0. So then we'll have the smaller values. Yeah. A smaller, then you can say second moment. Okay. This is because that if you have variable z, square is always bigger than some value a square. Okay, so next is a quick question 2. Okay. Any questions? Yeah, remember this series have a name, but I forgot the name. This poverty. So it can only be leader. Okay. So let's do question 3. Okay, we have a normal distribution. That's nice. And we have these two estimator. And this is the estimator for sigma. Okay, instead of sigma squared sigma. Okay. And want to find the asymptotic distribution. Okay. Okay. The T1 is easy because you can apply central limit theory. Okay. So by the central limit theory, we know the T1n will minus the mean of T1n has square root of n. They will converge it to the variance of T1n. So it should be the variance of this one. Okay. And by the hint, we know this value is equal to sigma, and the variance of this one is equal to this. Okay. This first part. The second part is T2n. So for T2n, we have to use the delta method. So this is equal to n squared. Okay. No. Okay. First, you know that this one will converge to the sigma square because the mean is 0. Here, mean is 0. So we will have next T2n minus sigma square. Okay. So by the delta method, this can be approximated by this, the summation of Si square minus sigma square, and the G of mu is G of sigma square is equal to square root. So we have to multiply this. Okay. So this is equal to like sigma. Okay. Yeah. Then we can use the central limit theory. So this is equal to normal, linear, and the okay. The variance part is the square of this, square of the first derivative multiplies the variance. The variance is equal to okay this. Okay, it's not. Okay. And we know that the variance of s bar s squared is equal to 3 sigma to power 4. Because this is a normal distribution, so this is equal to 0 and 1, 2. Okay. Okay, so we have the asymptotic distribution for the two different wafers. Okay. So we can figure out which one is better. Okay. For T1 is pi 2 minus 1. Okay. And for T2n is which has better 1.6. So this is approximately 3.14. So this is so this should be 1.6 minus 1. So it's 1.6. Yeah, so this one is greater. It's better. Okay. 3. Okay. So 1/4 squared is smaller than so T2n is better than T1n. Okay. And this for B. Okay. You can see this one is much easier than compare the method in question 2 for mu equal to nino. That is because for question 3, this 2 is totally unbiased. The only difference is the variance. But in question 3, question 2, part C, the asymptotic distribution is not it's biased. Yeah, this one is biased. Okay, so it's a little bit more complicated. Okay. So if you have a bias estimate or bias asymptotic distribution, so for example, if the T1 converges to some normal distribution with so then we will use the mean square error. So there will be mu square plus sigma square. We will compare by mean square error. Okay. So like this. Okay. Okay. Any questions? So if you don't have questions, I think that's today's discussions. And let me know if you need any help.
Chi,
Okay.
maybe in question 3,
Okay, question 3.
I don't know if there's any problem or any typo with the 2 and the n in the denominator. In the solution, I mean.
Here?
If you go up a little bit, I think.
Okay.
I think it's at the beginning of your answer to 3.
Okay. Let me see.
Yeah, here. So you say bicentennial limit theorem, and then the thing that you subtract, you say pi divided by n, but I think should be 2, but then the n is missing, or?
Let me think. Yeah, it's typo. Thank you. So this should be 2. Yeah.
And the n should
That is also 2. Okay. Yeah, thank you. Yeah, that's
you
right.
okay, but you should still divide by n, I think, right? Or not?
You mean divided by n? Oh, okay. You can say like this is like this. So n is in here.
Oh, okay.
Yeah. So this is a mean. Yeah. So it's a
Okay, I see.
small mean minus mean. Yeah.
Okay, thanks.
Yeah. No problem. Yeah. Okay. Yeah. I see this question. If they ask you to calculate this and this, they will have a lot of calculation. Yeah. It's very less they give you the solution. Okay. Any more questions?
Thanks very much, Chi. Have a good weekend.
Yeah, you too.